So, folks, can you all listen up? We're going to be doing a lesson on the Atwood machine, but normally I do a demo at the end of this lesson. I'm going to start. So can you, in the lesson, turn near the end of the lesson where you see a lovely picture of a bucket of water, example 6. Find this. And this is going to be our thought experiment. And then we're going to try the experiment. And this may involve two of our finest and best getting a little wet. So here is the question. It says this. A water bottle is drilled with many small holes so that it leaks when it's filled. If I fill it up and I drop it from a height, while it's falling, what happens? A, the water stops leaking out. B, the water keeps leaking out at exactly the same rate. C, the water leaks out at a slower rate. And D, the water leaks out faster. And we're going to do this experiment in a second. But what I'd like you to do right now is put a star next to the one that you think is the correct answer. If I have a leaky water bottle and I drop it, A, will the water stop leaking out? B, will the water leak out at the same rate? C, will the water leak out at a slower rate? Or D, will the water leak out at a faster rate? Okay. And then we're going to add a part 2. So the very first part of the experiment is going to be me dropping it from a height. The second part of the experiment is instead of me dropping it from a height, I'm going to start from ground level and I'm going to throw it up. On the way up, while it's on the way up, do you think A, the water stops leaking out, B, the water leaks out at the same rate, or C, the water leaks out at a slower rate, or D, in fact, you know what? I think it's the number 1 from your homework is what I'm talking about. So if I fill that same water bottle and I throw it upwards, what do you think? A, B, C, or there is no D this time for some reason. Anyways. Okay. Put a star next to what you think the correct answer is. And then we're going to do the experiment. The correct answer is A. Why? 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 Is there a way I could have predicted that ahead of time using principles of physics? Shelby's nodding. Convince me, Shelby.
The bottle and the water are falling at the same acceleration.
Okay. Let's even be more specific. Here's the water. Here's the bottle. When I was dropping it, what was both of their initial velocity? 0. Okay. What was their acceleration? For both of them? So if they start with the same velocity and they accelerate with the same acceleration, is it possible for one to get ahead of the other? No, which means, because for the water to leak, either it has to get ahead of the bottle, or the bottle has to get ahead of it. It's either going to leak behind or leak ahead. Okay. But wait a minute, Mr. Dueck. How does that explain when you threw it up? What did we notice when I threw it on the way up? It also stopped. How the heck? Wait a minute. Shouldn't the bottle and the water... Okay, still same acceleration of negative 9. Oh, and did they also both start again with the same initial velocity? This time not 0, this time whatever it left my hand at. So again, same initial velocity, same acceleration in the opposite direction of the velocity. Then yeah, I guess the water can't get ahead. We could, in theory, do that with an open bucket. The only problem is the catch at the end would spill a lot of the water. I haven't thought of a way to do that safely with a bucket of water. But if I went skydiving with a bucket of water, the bucket and the water should, as long as it doesn't start tumbling, should stay together. Now, if we got to a really, really fast speed, there may be a slight vortex created behind the bucket. And so, okay, maybe my physics at a higher speed won't quite work as cleanly because there could be turbulence and things create. Okay, it's more difficult. But for now, okay, all right, I'll go with that. I'll go with that. So says, using principles of physics, explain your answer. I think we did up here, and I think really, if I want to explain it for on the way up, all I would do is say, therefore, the distance, its displacement at any point in time has to be the same for both of them. Has to be. There's a lovely no English physics chart explanation. Let's go to the beginning of the lesson. The Atwood machine. I think what's going to happen is I'm going to start the lesson now, and then I may finish this lesson on Monday and start half a lesson the following. Because I can't fall too far behind. We'll see. Play it by ear. The Atwood machine. The Atwood machine is a name for a pulley system as seen below. If you imagine this middle block is a pulley, this is an Atwood machine. When one goes up, the other one goes down. And there's some beautiful physics behind it. This is also, for example, how elevators work. All elevators have a counterweight. That's the mass of the elevator empty. So the motor is only lifting the people, not the actual elevator car. It's much more efficient that way. So we have mass M1, mass M2. Mass M2 makes it easier for a person or a motor to lift mass M1. Mass M2 is called the counterweight. So here's our first question. Suppose we have equal masses and they are placed on both sides of, I should also point this out. We're in our magic physics world. Do you know how much these ropes weigh? Nothing, because that would make the math yucky. Do you know how much this pulley weighs? Nothing, because that would make the math yucky. Do you know how much friction there is in this pulley? None, because that would make the math yucky. So this is a theoretical construct. So think really, really well-greased, really light pulley, and somehow magic ropes with no mass. So, had to point that out. Equal masses are placed on both sides of the Atwood machine. And one mass is lifted up, lifted higher. So what we're talking about, imagine there was no friction here. We're talking about this. One mass is lifted up higher. If there was no friction, if this was perfectly frictionless, and if these ropes had no mass, if I release this bottom one, what will happen? A, the system will remain at rest. B, the higher mass will fall down. Or C, the lower mass will move lower. Once again, we're going to vote. Once again, how high you hold your hand up is how sure you are of the answer. Okay, so here's our situation. Who says, Dueck, A? It's got to be A. Oh, some. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Who says, Mr. Dueck, the higher mass is going to fall because things fall down to the ground? B. No one. Oh, 2. Who says, no, Mr. Dueck, that lower mass, since you already got it down, it's going to want to fall down lower? 1, 2, 3, 4, 5, 6. You know what? This is a job for something. This is a job for a free body diagram. So I'm going to zoom in on this picture right here, and I'm going to say, okay, what are the forces acting on the left-hand mass? Get the obvious one. Is it in free fall? Is there a rope? Oh, so tension. What are the forces acting on mass 2? Get the obvious one. Now, you'll notice I didn't call it mass 1 and mass 2 because the masses are the same. I got really lazy, Ryan, and I just said I'll use M's for both of them because apparently they're interchangeable. It does say the masses are identical, right, in the question, right? Yeah, okay. Tension. Now, some people thought, those of you that voted C, if the higher mass is going higher, that must be your winner, because that's what's pulling everything down. Let's make that the winner and see what happens. So we're going to pretend this is the winner. Come here. Come here. Change colors. This is going to be our winner. So anything that ends up pointing down when it gets to the right-hand side is going to be winner plus. Anything that ends up pointing up on the right-hand side is going to be loser minus. So we're going to have this, winner. And then I run into tension, it's a loser, because it's pointing up. Now, you might think this tension is a loser as well, because it's pointing up at Emma. If I follow it, when it gets to this side, which way is it pointing? Which is winner. And you might think that this mg is a winner because it's pointing down, but follow it. When it gets to this side, which way is it pointing? So it's a loser. Have I written forces from more than one mass in my equation? Yeah. Well then, I better go what do you notice? Losing tension. But wait a minute. What else? I lose those two. In fact, this left-hand side works out. How would I get the A by itself? You know what? Those two masses are identical. I could just say divide by 2 m's. What's my acceleration? So what's the correct answer if my acceleration is 0? It has to be. It says, let's write down A equals 0. Explanation, there it is. I went to a good free body diagram. If my masses are identical, it won't move. By the way, or they could keep moving at a constant speed in a straight line if I set it up that way, because all it says is A is 0. It doesn't say V is 0. So I could have, if I really wanted to be nasty, Marissa, started them both moving at a constant speed and let go, and they should have continued until we ran out of rope. What if the masses are uneven? Then you're going to accelerate. Example 2. In the diagram below, assume M2 is 5.8 and M1 is 2.3 kilograms. A says, solve for the acceleration. B says, find the tension in the cord. What do they want me to find? Acceleration? Any suggestions on how I should start? What might this be a job for? Although, again, technically, Jake, I'm really not doing a free body diagram because I'm not rewriting everything. I'm going to label the forces on the lovely diagram that they gave me. Okay. What are the forces acting on mass 1? Get the obvious one. What else? There's a rope. What else? Is it touching the surface? So no normal force. If it was touching the surface, I might have to take that into account. But it's not, so okay. They put that gap there deliberately, I assume. Friction? No, we're in our magic physics world. This is a frictionless. Okay, so what are the forces acting on mass 2? Get the obvious one. M2G? What else? Who's winning the heavier mass? Which one is that? Okay, this thing is going to accelerate that way. That's my winning direction. So any force that ends up pointing down when it gets to the right, Rachel, is going to be winner plus. Any force that ends up pointing up when it gets to the right-hand side is going to be loser minus. M2G, I have a minus tension. And again, Ryan, every year I have some kids that say, isn't this tension pointing up, so it's minus? Follow it around. When it gets to this side, which way does it end up pointing? Down, winner plus. And follow the M1G around. When it gets, it ends up pointing loser minus. Have I included forces from more than one mass? Then I better include more than one mass. All together now, let's relax. Hey, Ty, what are they asking me to find in part A? Oh, hey, folks, how would I get the A by itself? Now, I do like the Atwood machine, Ty. The setup is a bit tricky, but the actual solving, yeah, divide, and you got the A by itself pretty quickly. A is going to be M2G minus M1G divided by M1 plus M2. It's going to be M2 5.8, G 9.8, minus M1 2.3, 9.8, divided by 2.3 plus 5.8. Once again, I strongly encourage you, try this on your calculator, because every year I have kids that write this on the test and then have the wrong acceleration because they didn't make their dumb calculator mistakes in class. Is there more than one number on the top? Brackets. Is there more than one number in the bottom? Brackets. I would type it like this. Open the top. 5.8 times 9.8 minus 2.3 times 9.8. Close off the top. Divided by, open the bottom. 2.3 plus 5.8. Close off the bottom. I end up with 4.23 blah, blah, blah. I'll write 4.23, but I'll store this on my calculator. Units, meters per second squared. And that's my answer for part A. What about part B? What does it say? Find tension. Okay. Look at one mass. Which one? Doesn't matter. Although, I would pick the one in which tension is a winner. Mass 1? Can you give me the equation, Alex? Give me the whole equation. Equals. Oh, because we're only looking at one mass. How would I get tension by itself? Now, you could go M2G minus tension equals M2A. And you could still get T by itself, but humbly I suggest the left-hand equation a little easier. How would I get T by itself on the left? Yeah. So tension is going to be M1A plus M1G. It's going to be M1, 2.3. A. I'll write 4.23, but I'll use the longer value, plus 2.3 times 9.8. You get 32.3?